Okay, so first off, we're going to start with Daniel Baxter. Daniel is a bridge department manager at Michael Baker's Minneapolis office, where he also serves as a project manager and a senior bridge engineer. He has been involved in both rehabilitation, design, and load rating of many complex bridges, such as 3rd Avenue Bridge, Winona Bridge, High Bridge, Franklin Avenue Bridge, Lafayette Bridge, and Hastings Bridge, all over the Mississippi River. He's also recently led the analysis of 18 existing pier caps with sectional and strut-and-tie methods and helped develop procedures for the design of 38 new pier caps using the strut-and-tie method. And we also have Shayla Olson, who is also an engineer at Michael Baker's Minneapolis office. She has extensive experience in pier cap strut-and-tie modeling, performing both new design and load rating utilization with MIDAS Civil and post-processing Excel spreadsheets. She graduated with a bachelor's in civil engineering from the University of Alabama at Birmingham in 2014 and got her master's in civil engineering from the University of Colorado in Denver in 2016. She's a licensed professional engineer in both Minnesota and Colorado. So without further ado, I'm going to share my screen and hand it over to Daniel. 1 second. Okay, Daniel, you should be able to share your screen now.
Okay, great. Can you see my screen?
Yep. Oh, and sorry, just one more thing.
Can you hear me okay?
Yep, perfectly. Just one more thing I wanted to mention for our audience. If at any point you guys are unable to see Daniel's presentation clearly, you should be able to see a little bar at the top, right underneath the webcam where you can slide it up and the presentation itself will increase in size. Back to you, Daniel.
Okay, great. Well, thank you, Lucy, for the introduction, and thanks so much for having us present today.
Thank you, guys. We're very excited.
Oh, great. Well, hopefully you'll still be excited by the end of the presentation. We'll see. But the first part of the presentation here is we'll start by talking about the different types of models you'll need for strut and tie analysis of a pier cap. Then we'll move on to discuss some pointers, general principles of developing the strut and tie model geometry for pier caps. Then we'll talk about what's probably, at least in my opinion, I think the trickiest part of the process with pier caps, which is calculating and applying the loads and reactions from the superstructure correctly, and making sure that those forces are consistent with the reaction loads at the piers. So for this discussion, we'll go into a bit of an example showing how to work through that process at one location using MIDAS Civil and the moving load tracer functions of it. Then we'll go on to a discussion of performing specification checks, and then I'll close with the discussion of like why it makes sense to use the frame model method, which I'll show everybody to obtain the reactions that you apply to the strut and tie model. And then Shayla will go over a load rating example for a pier cap in some detail after I'm done. Okay, well, one thing about this presentation, since unfortunately we don't have all day, so it assumes that you probably have some knowledge of strut and tie analysis and what it is going into this. Big picture, in case anyone doesn't, the general idea here is that we're visualizing the flow of forces through essentially any type of concrete element as an internal truss, where the tension members of this internal truss are termed ties in strut and tie analysis. The compression members are termed struts, and the joints where they meet together are called nodes. And one nice thing about this method of analysis is it's suitable for regions of concrete structures in the vicinity of the application of concentrated loads or geometry changes, where oftentimes the beam theory sectional analysis methods we're used to using are not applicable because of those concentrated loads or geometry changes. But good news is strut and tie analysis is applicable everywhere. So that being said, let's talk about the different types of models we like to use to analyze pier caps using strut-and-tie method. Well, probably big picture too is you may ask, well, why use the strut-and-tie method to analyze pier caps? And then the answer is that pier caps, most of them are subjected to concentrated loads from the superstructure, where the superstructure girders are supported on bearings, and so that the distance of like the member depth essentially the member depth extending each side away from one of these concentrated loads is quantified by the LRFD code as being a disturbed region where beam theory isn't applicable, but strut-and-tie analysis is. So that's why we want to use the strut-and-tie method for designing pier caps, now following the current LRFD provisions. So our method of doing this essentially includes two different types of models. The first is just a simple frame model of the pier cap that's being analyzed plus the columns. This frame model can be modeled with beam elements using structural analysis software such as MIDAS. And depending on the complexity of your structure, you may or may not want to include the superstructure that is delivering the loads to the pier caps in the analysis model as well. We'll talk more about that soon. And then the second model that we used with this analysis is an actual strut-and-tie model of the pier cap, which is modeled with truss elements, which also can be done with MIDAS Civil software. And the geometry of the strut-and-tie model then is typically determined just before you make it for the first time. But the strut-and-tie model itself tends to be really simple. It's just a truss model modeled with pier caps, where the form of the model represents that internal truss that we are using to visualize the flow of forces through the pier cap. So we'll have these two different models: frame model of the entire pier capping column and a strut-and-tie model of just the pier cap itself. So really the first task then in developing one of these models is to determine what the geometry of the strut-and-tie model of the pier cap should be. So there's some initial guidelines we can follow to just start laying out this geometry. We know that top and bottom ties will be placed at the center lines of the top and bottom longitudinal steel, because we're going to use the forces in our ties to directly design the reinforcing steel. So for our longitudinal steel, we'll want that tie to be placed at the center line of the longitudinal bar group, whether it's top steel or the bottom steel. And these are and I should add that it's the center line of the longitudinal bars that are assumed to act as part of the tie. You'll also have some longitudinal crack control reinforcing most likely, but not all those bars necessarily will be included in the tie. So you'll just want to place the geometry of the model at the center line of each bar group that is going to be included in your tie. So we know that when we're developing our model and we're figuring out our boundary conditions and nodes, so we mentioned that our top and bottom ties, so the chords of our internal truss, are going to be placed at the center line of the top and bottom longitudinal reinforcing steel that's being used for the tie. And we know that nodes in our model are going to be placed at the intersection of where the girders and the bearings from the girders are placed on the pier cap. So we know that we'll need nodes at those locations. And we're also going to place nodes in the model where the model intersects the columns. So just where those go depends on whether you're considering the columns to be fixed or pinned to the pier cap. Different states have different policies about this. But for this discussion, we're going to assume that they're fixed, and that for the rectangular columns we're using, it's sufficiently accurate to place those nodes at the quarter point in the column width. So with two nodes, that allows there to a force couple to be transferred into the cap at each column so that we have our fixed column condition. So these guidelines just give us some general a starting point about where we're going to lay out our key nodes that can't be moved, because we know we're going to have nodes where the bearings are, we're going to have nodes at the column support locations. But then this still leaves open the question of, well, where do the rest of the nodes in the model go, and where do we place the vertical parts of this internal truss and the diagonal parts? So let's talk about that some now. Well, there's some general guidelines we can follow. One is to just follow the most direct load path. Typically, the most direct load path is going to be the most accurate. And we also want to follow what's called the 25-degree rule in AASHTO LRFD, which is that the angle between where strut and tie, or just any two members intersect at a node, shouldn't be less than 25 degrees. Another thing we like to follow when we set up the model is to use overlapping X diagonals. The reason for this is we set these diagonals to be compression only members. And for each tie that you have an element in tension, you're directly going to use that force in the tie to design your reinforcing steel. And typically we don't want to have diagonal bars and pier caps, so we don't want our diagonals to go into tension. And depending on the live load case, because there are a number of different live load placements we'll need to consider on the superstructure, some diagonals could potentially go into tension, some could go into compression. But by using overlapping X diagonals and defining them using MIDAS, which can do this as compression only elements, it then orients the angle of the diagonal so that they're all in compression for different live load cases, and typically only one of the two overlapping diagonals will have any force, and the other just will be a zero force member that doesn't do anything. So we find that's a pretty convenient way for both the designing and new bridges, new pier caps, and analyzing existing ones for load ratings. Let's look at let's return to this discussion of the 25-degree rule and looking at some different ways we would want to set up the diagonals in the model when we're determining our model geometry. So the models with a red box around them are not what we want, while the ones with the green box are. So in the top left image here, we have two bearings that are slightly offset for each span that then have an angle between them of 6.2 degrees, which we don't want because it's much less than the 25-degree rule. But then if we look on the right, what we've done to solve that problem is simply to just resolve the node that we use at the bearings to just be the average distance between both, so that there's not we don't use two diagonals, we just use one, and that solves our 25-degree rule problem that we had on the top left here at the top right, because now our angles are much larger than 25 degrees. And that would also come into play when we look at the center image here, where we have two closely offset bearing lines where the girders at each adjacent span don't completely line up. And if we draw verticals underneath those, then the angle between the vertical and the diagonal is 16.5 degrees that we don't want. So then resolving those two verticals into just one member of the truss that's at the average distance between both bearings, as we've done on the top right, gets rid of that problem. So typically, the most efficient layout is going to have the fewest number of vertical members in your strut and tie internal truss, but that's going to be governed by the 25-degree rule too. So at the bottom left here, let's say we drew a diagonal from this average bearing point here. I'm not sure if you can see my cursor or not, all the way over to the right side of this model. But then if we measure the angle between that diagonal and the bottom chord of our internal truss, it's 17.4 degrees. That's less than 25 degrees that the code specifies as a minimum. So we know that then we need to break up this panel into this big panel into two sub panels. And then once we do that, as shown at the bottom right, then our angles between the bottom chord and the diagonal are 31.8 degrees, above 25 degrees. So we're good in this case. So just a few examples here showing some of the considerations in setting up your strut and tie models geometry. So some may be necessary here. I mean, once you have these like column and bearing nodes, that shouldn't change. Since we do want to place, again, the reinforcing at the ties at the center line of the reinforcing, particularly for the chords, you may need to do some slight iteration as your design progresses if the center line of your reinforcing group changes slightly. But it's easy enough to just translate the nodes in the model and shift those around. So it really
Daniel? Daniel? Sorry. Oh, I don't think he can hear me. Daniel, can you hear me?
Like number and size of bars is going to be pretty close to
Daniel,
what you'll end up
sorry.
getting. Yeah,
Can you hear me? The audio just cut off on your end for about like a minute or so. Do you mind just um going back a little bit? It just completely cut
sure.
out.
Oh, can you hear me now?
Yeah, I hear you clearly.
Okay, sorry about that.
No.
Let's see. What do you remember? What the last thing I talked about was?
I think it was it was probably like the last 3 points you mentioned. I can't remember
Daniel,
exactly.
I think it
Okay,
is the next
Uh,
slide. The
yeah,
next
it
slide.
was at the beginning of the next slide.
The
okay.
slide
Oh, so
6.
Yep.
so it's slide 6. Okay, so every you guys heard everything on the previous slide.
Yes.
Okay, great. Okay, so back to this slide. So forgive me if you've already heard some of this, but so now that you've got your sort of basic nodes where at your bearing points, at your column locations, those shouldn't change. I mean, once we've worked out the geometry, some iteration may be necessary, particularly the distance between the top and the bottom chord. Since, as I mentioned, the locations of those chord elements are going to be at the center line of your reinforcing group. As your design progresses, you might have some, changes and bar sizes that could move those distances around a little, but that's easy enough to adjust your model just by translating the nodes, and shouldn't be that big of a hassle. And people sometimes ask, like, hey, what's a good way to get started in terms of assuming where those chords are located? And I'd say like a good way is to just find some prior plans for previously designed pier caps. Even if those pier caps were designed with sectional analysis, which they probably were, the change to strut and tie analysis typically isn't large enough to just make the longitudinal reinforcing requirements completely different. So I would say like previous plans should provide a helpful guide as to estimating, say, how many rows of reinforcing you might need at the top and bottom, and how large those bars will be to just get you started. And then again, if you have to iterate, it's not a crisis, because it's pretty easy to just move the translate and move the nodes around. A little word about efficiency of the model here. And generally, as I mentioned previously, the fewer vertical ties you have, the more efficient use of materials you'll have, because your vertical force gets passed through the truss to each tie. So the more ties you have, then the more force you're going to have to design for. In this example in the top left, this force P, half of that force is taken to the right support, and just through the mechanics of trusses, like that half of the force is going to be in every vertical tie. So the fewer vertical ties you use, then the less reinforcing steel you'll need, since the force in each vertical tie will directly correspond to the reinforcing steel that's provided in the design. And on the right here, we do have an example just showing how with the bearing locations here and providing like verticals with diagonals, that I think in this case the 25-degree rule wasn't met, but we solved that by just getting rid of one of these subpanels and having just a direct diagonal strut from that center load straight into the column. So that's another technique that can be used. So here's an example of a final model for a pier cap that follows these principles to satisfies the 25-degree rule. So again, the purple dashed elements, those are compression only elements, so that we don't have any diagonal tension members that would require diagonal steel, which isn't typically used in a pier cap. And again, in each panel, only one of those two members will typically see force. And also to just keep the geometry reasonable, there might be some members that are basically vertical, but if need be, slightly inclined, so that we don't need to introduce subpanels that would violate that 25-degree rule. Okay, so then once we have determined the geometry of our strut and tie model for the pier cap we're designing, then the next step is to construct the strut and tie model itself. So typically we'll do that by just getting the coordinates for the model from microstation. Again, we'll construct this out of truss elements. We'll using, again, compression only elements for the diagonal members. And this is an important consideration, we want the boundary forces that are applied to this model at the columns to be consistent with the forces at the top of the columns themselves. This is actually an AASHTO requirement to have the boundary forces be consistent. And we also want to make the model internally determinate if we can. So the way we do that is we actually only have two fixed boundaries for these models, like one pin and one roller. And the rest of the reaction forces we compute from the frame model and apply to the strut and tie model as reaction forces. We'll talk about this in some detail because it's not, I would say it's not super straightforward about how to do that. And then we also apply our loads from the superstructure for our different live load cases to the strut and tie model. So this gives us two sets of loads, the superstructure loads, and then the support reaction applied loads. So we'll talk about how to find both of these in some detail. So let's go through the process now of calculating and applying loads to the strut and tie model. First step is to calculate the dead and live loads from the superstructure. Then our second step is going to be to apply these loads from the superstructure that would be at the bearings of the pier cap to a frame model of the pier cap and the columns. Then the third step of this process is to convert these frame model top of pier axial forces, moments, and shears into nodal reaction loads that we apply at the boundaries, the strut and tie model at the support nodes. And so then once we have those loads in there, we'll apply our concurrent superstructure and reaction loads to the strut and tie model, and design the steel we need, perform the checks we need for a new pier cap, or compute rating factors for an analysis of an existing pier cap. Okay, so let's start with the first step here of calculating dead and live loads from the superstructure. So to do this, we want to use the simplest possible method we can use and have it still be reasonably accurate. So the easiest method to use is just to use what's called the lever rule, unless a more complex analysis is needed. And typically the lever rule will work just fine if your superstructure is straight or only slightly curved and it's supported on bearings. The second option, if the lever rule doesn't work for us, is to create an analysis model. You can with MIDAS Civil that includes both the superstructure and the piers. Some cases where this is necessary is where the superstructure is, say, significantly curved or significantly skewed, or integral with the piers where the lever rule can't really be used that accurately. So let's talk about applying the lever rule. So I think most people are probably familiar with it, but the general idea is that in the transverse direction, you consider the deck to be simply supported between girder lines, and then you just use a line girder analysis to determine the tributary length of loads on each supported superstructure span, and you use just different live load placements that then maximize these reaction forces from our deck at the girders while following the AASHTO rules for lane widths and vehicle placement and multiple presence provisions. Some people I think sometimes get a little intimidated by setting this up, but it's really not that. It's less complex than it may look, and I think you'll find once you get into it that you may need to consider fewer live load cases than you might initially think. That it often becomes evident pretty quickly which live load placements and cases will control. So if you can use the lever rule, I highly recommend doing so. But then there are cases, this is a bridge we recently analyzed, a bridge with a significant skew, with a girder line that stops at a pier, and cross frames that are oriented at a different direction than the piers, and varying span lengths, where we didn't really think we could use the lever rule accurately to find what the superstructure reactions should be that are applied to the pier cap. So what we did is we included the superstructure model and the piers in the same analysis model, and then used the superstructure model to determine what those bearing loads from the superstructure should be. Now, one thing to keep in mind is for this whole procedure, using the frame model to determine boundary forces to apply to the strut and tie model of the cap, for this to be accurate, all the live load forces for each different case need to be concurrent with one another, so you can't use a live load envelope. So the example I'm going to show is how to use MIDAS to determine these concurrent live load faces for concurrent live load cases for the live loading that maximizes what would be shear and negative moment at the face of the pier cap here. So let's zoom in to where the blue boxes. So what we're trying to do is in the element that has the box around it is to figure out what the live load is that maximizes what would be the vertical shear and negative moment at the face of the column, and then to define that as an equivalent static load case so that we can be sure the loads from it are concurrent. Well, you might be asking yourself, hey, didn't you say that sectional analysis wasn't valid? Why are you talking about shear and moment? But in general terms, the loadings that in a sectional theory would maximize shear and negative moment are going to be the same loadings that would maximize the force in the vertical tie or top tie steel at those locations. So we can use those sectional forces to figure out what our live load placements should be as we go along the length of the cap. So for this example, we're interested in what the maximum HL93 shear and negative moment is in this element 30053 part I that has the box around it. So if we zoom in and look at the element number, so you can see 30053 in the pier cap here that's right at the face of the column and has a bearing from the exterior girder just to its left. So if we take the render view off in MIDAS and then turn on the local element direction, it's a little hard to see on the slide, but the arrows for the local element direction are pointing to the left. So that tells us that the right side of this element, 30053, which is located at the face of the column, is at the face of the column is going to be the I end of the element, and then the left side is going to be the J end of the element. But in this example, we're interested in the loading at the I side of the element, so that's why I've denoted this as element 30053I. Okay, so the first step here is to determine which live load case controls at this element. So you can go to just on the ribbon, the results tables for beam forces. Then you'll type in your element number you're looking for. And then, typically for a model such as this, you'll have defined a number of different live load cases with different lane patterns, maybe some like one pattern force to the left parapet that follows the left parapet as closely as AASHTO allows, another pattern that follows the right parapet, other lane patterns that have like a wheel centered on a girder line and so forth. So just select all the different individual live load patterns you have at part I, and then just click OK. And then you'll have a list of the forces at this element for all these different live load patterns, and then you can just visually figure out which one of them is maximizing shear, be it positive or negative shear, and which one is maximizing negative moment. So it so happens that in this case, our case 2 here, with the double truck, since looking at HL93 loads, this is a reaction at an interior pier, so the double truck would be indicated here, can be included here along with the truck plus lane and the tandem plus lane. So this particular case, it seems like a slam dunk that our case 2 live load pattern here controls for both shear and negative moment using my frame of the superstructure plus piers in the frame model here. So since I know that, now my next step is to go to the results ribbon here and use the moving load tracer. So in the moving load tracer, I'll just have like written down on in a notebook, say that it's case 2 with a double truck minimum control. So that's the moving load case I'll select. Then I just type in my element number I'm interested in here, 30053. I'm interested in part I right at the face of the column, and I'm interested in the loading that maximizes minimum negative shear, so I click FZ right there. And then the nice thing is that once you hit apply, it then visually shows you the position of the vehicles that does this. And this is a real nice way to make sure you've defined your lanes correctly too, because you can look at them and see, like, do you have the required offset from the parapet? So in this case, it's telling us that actually, even though we are considering the double truck, it's actually just the truck itself that controls with just 2 lanes due to multiple presence factors most likely, and it shows you where to apply the lane load. The colors here, what it's giving you is the influence surface for this element, so it just shows you how it's applying the HL93 loading to the influence surface. So assuming this looks good, things look reasonable, then to define this as a static load case, then you'll just click write the min-max load to the file. This window clicks up. MIDAS generates sort of a default file name based on the element you specified. It's kind of long though, so I like to rename it to something that still tells me what. I like to rename it to a shorter file name that still tells me what this vehicle is doing and where it should be applied. And so once you do that, then and click OK, this text editor comes up, which gives you the definition of the static load that we're applying for each vehicle. Here you can see the file name that you've defined, that you've saved it as. You'll want to make sure that your units here are consistent with the units in your model that you're working in. Then you can just type in whatever you want the name of the static load case to be. So we're defining this truck as a static load case so we can be sure that all the forces in the frame model will be concurrent for this one loading that we're looking at, or else the statics won't work. So just make sure the 2 lines here have the same name, because they need to be the same, and that's going to be the name of our static load case. So if we do that, then we save that text file, and then we go to the tools ribbon and open up the MCT command shell, and then you can open a file right there. So we'll open that text file we just made and hit run, and then what it does is then it adds this case as a static load case to the rest of the other static load cases that have already been defined in the model. So you can see it right there. So now we're able to, by adding this static live load case to the dead loads, we're able to get concurrent loads for each different case that we'll want to use for our strut and tie model. So if you were doing this, you can imagine how you would just march across the length of the pier cap, looking for the forces that maximize negative and positive moment in the frame model, and maximize shear at the faces of the columns, and then you'd end up with a number of these static live load cases, so you can look at different concurrent live loads. And so now just a little bit of a word about comparing the envelope forces to this live load case, the static live load case we've just defined. For this pier cat in our model here, if we ask for the minimum HL93 load from all the different, from an envelope load combination of all the different live loads, this is what we get. And then if we compare it to our static load case, we can see that the shear loading is exactly the same in the element of interest, which I've highlighted in red, that 30053, right at the face of the column. So these are the same, but then you can see that the bottom one here, this is, these loads are all concurrent for that truck loading plus lane loading we just defined as a static load case. So you can see that it's quite different along the length of the pier cap than the envelope loading would be, which should make sense. But it's making sure these 2 forces are the same from the envelope and the static case at the location of interest is a good check to make sure the analysis has been done correctly. Now for other cases where you can't use the lever rule, another is if you have integral caps, as was the case for this bridge. So we made just a full grid model of the piers for analyzing the pier caps of this bridge. This was for a load rating in Duluth. This was probably one of the more complex cases you might run into for this type of load rating, because we needed to carefully consider how the live loads were applied to this single point urban interchange. But it's just an example of how you can integrate the caps and superstructure, even for something fairly complex in the same analysis model. Okay, so that was our discussion of computing what the superstructure loads just to compute them. So now that we know what the loads are, the next step is to just apply them to a frame model of a pier. This will be done automatically if your piers and superstructure are in the same analysis model. But if you've used the lever rule, then it's more of a manual process. So probably the first thing to discuss here is just how you construct the frame model itself. Typically, we'll have a fixed support at the column to footing interface. We'll have a rigid elastic link to model the depth of the cap over the pier. We'll consider the fixity between the column and the cap. We're using fixed piers here, but if you're in a state where that's pin, then you'd use a pin connection. And so that this method works correctly, you'll want to be really careful to use a consistent element local axis direction in the column elements. So the local axis for each column element and frame element and cap element should line up. And you can display the local axis in MIDAS to make sure that's working correctly. So to construct the pier frame model, this is a pretty straightforward model. It should be, we'll place nodes in the cap at the location of the superstructure bearings. We'll apply our superstructure dead loads and concurrent live loads, so just static loads for our different live load placements. Each different live load placement needs to be applied as a different static live load case so that the loads are concurrent. And we'll also, if the superstructure is included, we can just have a vertical element that represents the bearing, the appropriate bearing fixity conditions to transfer those loads into the pier frame model. Okay, so now the trickiest part likely is the third step of the process, which is to convert the frame model top of pier forces to nodal reaction forces for the strut-and-tie model. So following this procedure, it at first might seem a little complex. There's ways that sharp people like Shayla have figured out to automate this, and she'll talk about that more soon. But the result, as we've mentioned, is that you have an internally determinate strut-and-tie model, which is good so that you don't have to make assumptions about the stiffness of the elements that would shift the force around. And you also, perhaps most importantly, ensure that the forces you're in the strut-and-tie model are consistent at the boundaries of the model with the rest of the structure. So more precisely, that the forces at the tops of the columns in your frame model are consistent with the forces that are being applied at the tops of your columns to your strut-and-tie model, which is something that is highlighted in the part of Section 5 in AASHTO LRFD that covers construction of strut-and-tie models. So what we're going to do here is we're going to convert these frame model top of pier forces to nodal reaction forces to the strut-and-tie model. So what this does is this procedure resolves the moment shear and axial force at the top of each column in the frame model into a set of loads to apply to 2 reaction nodes per column in the strut-and-tie model. So we figure out what our forces are, axial forces, moments, and shears at the top of the columns in the frame model, and then compute what our reaction forces here should be to apply to the strut-and-tie model. So we're taking a close look at these forces, the tops of the columns, applying them to the model. So let's take a look at how you do that for this example 3-column pier. So again, at the strut-and-tie model, we're going to have 2 nodes per pier to represent a fixed connection. If we look at the top of column moment for one specific load case, we can resolve that moment, in this case 598.1 kip feet, into a set of 2 nodal loads that represent that moment, just the force couple from that moment, by taking into account the distance d between those nodes, which in this case is 2.5 feet. And just to make sure everything's working correctly, we can, if we then apply these nodal loads to just a single column model, we can verify that we get the same moment at the top of the columns in both the full frame model and just a single model where we apply those 2 reaction loads, I should say. For axial force, process is much the same. We have a total axial force here of 675.1 kips. We would just evenly divide that between our 2 nodal reaction nodes here. Same for shear. If we have a shear at the top of the column, we could just divide that by 2 and apply half of that shear to each of the 2 column nodes in the strut and tie model that represent the top of the column. Okay, so for this example here, so if we take the nodal loads that we've determined for moment, axial force, and shear and add them all together and apply them to the top of the single column model, just as a check, we should get a moment diagram, which is identical to the moment diagram in the right column here that we've computed the loads for. It's a little hard to read with just the symbols for the loads I've written, but if you look closely on the top of the column, you can see that moment is 598.1, so it matches what we had in the frame model. The moment at the bottom matches what we had there, so we know that we've computed these nodal reactions correctly, so that's good. So in general, here are just some basic equations that you can use to figure out what the nodal reaction load should be applied to each of the 2 nodes at the top of each column, just based on the axial forces, moments, and shears at the top of the column. So left and right nodes refer to the 2 nodes in the strut and tie model that represent the connection to an individual fixed column. So then one thing we'll need to consider is that these loads need to be equal and opposite when they're applied to the strut and tie model itself versus what you computed at the top of the column. So just be sure to flip those around. You'll want to do some checks when you do this at first, just to make sure your sign convention is consistent when you're applying these loads to the strut and tie model. So typically the side of the column that has more compression in them, your vertical upward load in the strut and tie model should be the larger of the 2 on the face of the column, on the side of the column that has the greater compressive force, or conversely, the side that is under more tension, compressive axial force has less axial force, where the axial force plus moment results in a net extreme fiber force on that side of the column that is more tensile than on the other side, and that reaction force in the strut and tie model should be less than on the compressive side. Okay, so now we've computed our superstructure and reaction loads, and now we can go ahead and apply them to our strut and tie model. So we'll keep in mind that the sign convention that we've been using, and again, when we make the strut and tie model, say in MIDAS, with we'll have just a pin and roller boundary condition, just 2, and the rest of the support reactions will be these nodal loads that we've applied. We need to be mindful of the restraints of each boundary condition. So at a roller, we would apply the shear, half of the shear, horizontal shear, because it can't resist horizontal shear, but at the pin, we would not. And one way to check that you've done this correctly is the reaction forces that you get at the pin and the roller should match what those theoretical nodal loads should be at that location, using the calculation procedure we just saw. So here's an example of at one node how you would do that. You just from the moment and axial force define the vertical component. The left node, at this case, the rightmost column is free, so we find a vertical force from the moment and axial force, and then reverse the sign to apply the strut and tie model. The right node has a roller support, so we don't apply a vertical load, but for the left node, we'd apply half of the shear to it, flip the sign convention from what you get in the frame model, 25.5 kips, and the right node, although it's roller, as I mentioned, it's free in the horizontal direction, so you'd apply the same force. And then you can compute that the reactions at the 2 support nodes should be equal to the point loads at these nodes, determined using the procedure we've seen. Okay, so that's, Shayla will go into that in a little more detail. Again, I find that's probably the most complex part of the procedure, but you can automate it with a spreadsheet where you just output the forces at the top of the columns that you get from MIDAS, say, into a spreadsheet, and then just using the distance between the 2 nodes, you can have that as an input. It can then calculate what these nodal loads should be, and then you can just copy and paste those nodal loads into MIDAS, so it will apply them to the strut and tie model. Shayla will show you how to do that. So let's talk a little bit now about just the specification checks that we would do to actually design our pier cap here. Now that we have the forces in our strut and tie model, let's start with ties. We'll need to design our top ties, our bottom ties, and our vertical ties, and we'll also need to check that the development length at the face of what's called the extended nodal zone, that the bars are fully developed. Code requires us that the reinforcing steel you're using for your tie needs to be fully developed once it gets past your node here at what's called the extended nodal zone, where it meets the edges of your compression strut. So the resistance equation for the strength of a tie, it's pretty straightforward. You can include pre-stressing if you want, but for most pier caps, it will just be the yield strength of the steel times the area of the steel you're using for the tie will give you your nominal resistance here. So your top ties, again, and your bottom ties, the area you'll use for those will just be the total area of the longitudinal reinforcing for each that's included in the tie. Typically for the vertical steel, the area that you'll use for those is the area of stirrups within the tributary width of each vertical tie in your model. So pretty straightforward, and by using these diagonal compression only members, you shouldn't wind up with any diagonal ties that would be problematic. So in this example pier here, that's what ended up working out. The horizontal tie area areas correspond to the horizontal bar groups that are spaced at the center line of the reed, and these bar groups, their center lines, correspond to the geometry of the horizontal ties in the analysis model, and the vertical ties use the area of vertical stirrups within the tributary width of each vertical tie for this design. So if we look at a cross section, the bars that are highlighted with the dark green circles are the top and bottom ties. You'll note that not all the longitudinal reinforcing is included in these tie areas. Touched on that a little bit previously. The rest of this longitudinal reinforcing would be to satisfy the crack control requirements, but it would likely be a smaller bar size than what you would use for your longitudinal reinforcing that's for the ties themselves. And then our vertical ties are shaded in green, and just the detailing of the stirrups ensures that they would be fully developed at the edge of the extended nodal zone too. Okay, so the specification LRFD also requires that we perform a nodal strength check. We need to only check the nodes at locations where there are geometric constraints, say like directly under a bearing, where the area of the node can't spread out. That's what's called a discrete node in a code. For say intermediate nodes that are away from say columns or bearings, there's a little more room for that stress to spread out, so that's called a smeared node, and you don't need to check the strength of those following the specification, because the idea is that you'd have more freedom to extend the geometry. So what we do with a nodal check is just to check the compressive stress at the face of the node. Really the limit is 3 compressive forces going into a node, so if you have more than that number of compressive forces going into a node, you can just find the resultant of several of them to then combine them into one for the nodal strength check. If you're using a new design, by providing the required crack control steel, you should be able to take advantage of the most favorable factors to satisfy your nodal strength check. Since the idea is that struts are typically bottle shaped, they're narrowest at the nodes, and they spread out in the concrete width between nodes, and then they narrow again at the next node. The idea is that if you satisfy the stress concrete compressive stress requirement at the node face, then you don't need to do there's no need to do a separate check of the compressive struts themselves, because the node is the controlling location with them for compressive stress. Shear serviceability is another check for new designs that's recommended. For hammerhead piers, it can be a little tricky to figure out what the shear span should be. Talking with the people who developed this equation, it's fine to take it from the nearest bearing to the face of the column. If you take it all the way to the nearest column node, that can make a pretty big difference in satisfying this shear serviceability check, and could force you into using an overly large hammerhead cap dimensions that would be larger than what current practice or past practice would say is fine. But this is just a check, the shear serviceability check, to make sure you shouldn't have any cracking or or like visible cracking really under service loads. But just something to keep in mind, that shear span distance A can be the distance to the face of the column rather than the nearest column node, and your distance D that's in this equation can be the average depth between the closest bearing and the face of the column. Okay, and really the last part of the specification check is providing crack control reinforcing. That's part of any strut and tie design. So the code, instructs us to provide both horizontal and vertical crack control reinforcing. The steel you've already used for your vertical ties, or counts towards that requirement too, as well as the longitudinal steel. But typically you'll need to provide, at least in the longitudinal direction, some additional steel to satisfy the crack control requirements. The maximum spacing between vertical bars is 12 inches. So in our diagram here for the Pier cap under consideration, the additional longitudinal steel we need is indicated by these dark green circles here. But the nice thing about this is also including this crack control steel should give us a real nice robust design that has minimal levels of cracking. Now there's some additional specification checks for Pier caps that it's a little, I would say it's not totally straightforward to figure out how to include them in a strut and tie analysis. We like to do an interface shear check at the top of the columns for longitudinal and transverse loads to verify that the column reinforcing has sufficient area to pass that check. A second check is that just about any cap supporting a pre-stressed concrete girder superstructure is going to have torsion in it, just due to the two side-by-side bearing lines. You can use the if it's checked, you can check if that torsion is below the threshold torsion, and if it is, you don't need to do anything about it. But if it's above that, you can use the equations in the code to figure out what your additional steel area should be to satisfy the torsional requirements. And it's okay to do that. It seems like, yeah, you're combining a sectional approach and a strut and tie approach, but the equations for torsion in the code assume that you're using are based on a space truss analogy, so they're based on a truss too, so it's okay to combine them, and that saves you from having to develop a 3D strut and tie model, which you probably don't want to do because the geometry gets complex and those nodes get complex. So it's a way to include torsion. And if you have transverse loads, say wind loads, you can just apply those directly to your strut and tie model, and those are fine. And your longitudinal loads for applied to hammerhead Pier caps. What we like to do for those is just use just a sectional approach to just check that all your steel on the vertical face, which typically is mostly crack control steel, can take that out of plane bending. So that should cover all of our typical Pier cap loads, as well as say, like longitudinal load from braking and transverse loads from wind. So the last part I just want to quickly discuss here is why use that frame model process I talked about to obtain reactions for the strut and tie model. Why not just put boundaries at each pier node in the model? I mean, that's simpler than making two different models and computing what these reaction forces should be. But the key is, I think it makes sense to use this more involved process so that you can ensure that at the interface of the columns and the strut and tie model, the forces are consistent between the two of them. And you can see that if you do use fixed boundary conditions at each column node in your strut and tie model, the results can be quite different than if you go through the process we went through to compute what these reaction nodal loads should be at the columns. So these two models here show the demands in the strut and tie model with the same geometry for one dead load plus live load factored load combination. So the same applied superstructure loads for the factored dead load plus live load combination. The top model has supports boundary conditions at each node. The bottom has just a pin and a roller, and then the calculated nodal reaction loads from a frame model to which these superstructure loads have also been applied. So if you compare the if you compare the force from the same load combination in both models, say at the tie here, at the top it's 19.5 kips, but at the bottom where we've computed what these forces should be to make every satisfy statics and make everything consistent, it's 121.3 kips. It's a fairly big difference. On the right side here, you see 82.8 versus 107.6. Some cases the forces are the same, but certainly not in all cases, like in the consistent model here. Another thing is, let's look at the top tension above the center pier. It's 220.9 here in the model with correct boundary forces, 151.5 in the full support model that doesn't have those consistent boundary forces. So at least in our opinion, these differences are large enough that it seems warranted to go through this extra step of also constructing the frame model and obtaining these concurrent boundary forces. Okay, so to summarize what we've seen, we've talked about using both a frame model and a strut and tie model for analysis. You can see in MIDAS Civil, we've developed the strut and tie model geometry, talked about some considerations there of coming up with the geometry for our internal truss that we're going to visualize the flow of forces with. We've talked about the need for concurrent live load reactions to make the statics come out correctly, and we've gone through an example to see how in MIDAS you can define static load cases that correspond to the controlling concurrent live load that you're looking for. We've talked a little bit about performing specification checks, and then had a discussion about why it's warranted to use this this multiple step process that also includes a frame model to obtain the support reactions to apply to your strut and tie model. So now Shayla is going to talk in a little more detail about how this process works for just one example pier cap that we were rating. And
Okay, thank you so much, Daniel. Wow, that was great. Give me 1 second. Okay, Shayla, you should be able to share your screen now.
Great. Can you guys see it okay?
Yep.
Okay, great. Let's see. So as Daniel mentioned, I'll just try and go pretty briefly through an example load rating of a pier cap using the strut and tie method that Daniel outlined, and using this MIDAS Civil software. So just a quick outline. I'll go through the models needed for the analysis, briefly into calculating and applying the loads and the reactions, performing some of those specification checks, and then a quick comparison of strut and tie and sectional method results, because for this example, we actually analyzed the piers with both methodologies and then compared the results. So first off, for the different models that we need for the analysis, this one happened to be a bridge that we used the superstructure model with the frames, with the piers in the overall longitudinal model. So that was one model, and then a second model was the strut and tie model for just the pier cap. So for the pier frame model, you can see we use these beam elements, and again, the piers cap and columns are all modeled within that superstructure of the bridge as well. So all beam elements, and then as Daniel mentioned, there's rigid links between the superstructure and the bearing elements, and then we've got these bearing elements, which represent the bearings that the girders are tied to. So, and then for the strut and tie model, everything is a truss element. The cross frame elements are all defined as compression only truss elements, and then the top ties, bottom ties, and then the vertical ties are all just truss elements. And then again, we're pinning the first column node, and then we have a roller connection at the last column node. And then we'll apply the girder nodes to match the same location as those girders applied in the frame model. And then column reaction nodes, which represent the columns into that strut and tie model. So in order to get the nodal loads that we need into the strut-and-tie model, it's a lot easier with the superstructure and frame model because you can just grab, for the dead loads, you can just grab the DC and DW loading taken directly from these elements in that overall superstructure model. So for the bearing elements to represent the applied nodal loads for the girders onto the strut-and-tie model, you can just grab straight these axial forces from these bearing elements that we have defined in our superstructure model. And then for the column reactions, as Daniel mentioned, you have to go through the process of combining the axial, shear, and moment forces at these column elements that you can pull from that superstructure model and into nodal loads that you'll apply to the strut-and-tie model. So for the girder nodal loads, again, you can pull the forces directly from those bearing elements. And then I applied the load factor. It was 1.15 for dead load per the owner, and then those nodal loads with the load factor applied will go directly into the strut-and-tie model to represent those girder nodal load forces. And then for the column nodes or the column reactions, these equations are slightly different than Daniel went through in his process, just based on the different orientation of the models that I had, as well as the different axes between the superstructure model and the strut-and-tie model. So it's always important to check these equations, or check your directions of your applied forces, and make sure that it makes sense, as Daniel mentioned. So, but again, these are just pulling that axial force, the moment, and the shear from the superstructure model column elements. And then I used Excel spreadsheets, since we had multiple different load combinations, and then set it up so that it can pop out these reaction nodal loads that we'll need for our strut-and-tie model. So here you can see again, I just used a spreadsheet and was able to set up a table in the spreadsheet so that I could copy directly from my spreadsheet and paste it directly into the MIDAS software, and makes it super simple, super easy when you have multiple load cases in order to copy and paste and make sure you have all of the correct applied nodal loads. Again, that correspond from the superstructure model and into the strut-and-tie model as well. So I just went through the loads, nodal loads, and then got the nodal loads tab open in MIDAS, and again, just copied and pasted directly. And one thing to note is, even if you don't have like moment X, moment Y, moment Z nodal loads, I didn't have any that I wanted to apply to the strut-and-tie model, but those, in order for me to just copy from the Excel spreadsheet directly into the table in MIDAS, had to populate something. Had to have some fill. So that's what all of those zero loads, and then again, just make it easy to copy and paste into the MIDAS model. So the live loads, a bit more of a process than just the dead loads. Daniel briefly went over this too, so it's a little bit repetitive, but hopefully it gives you guys some more understanding and can better grasp these concepts. So for the live loads, we had to pull the concurrent live loads, and we found those using the moving load tracer application in MIDAS. And then you can apply those as a static load case. So the first step is to find the maximum or minimum force and location of the force for whatever you want to look at. So for this instance, I was looking at positive interior moment, so between the columns, negative interior moment, negative cantilever moment on the west and the east cantilever, and then minimum and max shear throughout the entire cap. So what you're trying to look at may change versus what reinforcing you have in your cap. So if you have shear spacing, shear ties spaced differently throughout the cap, you might want to look at the worst case shear in the location of the largest spacing, and depending I guess in different groups of spacing along your cap. But every every instance that you want to look at is a new live load case. So it's important to keep in mind, you want to pick the controlling ones, I guess, is the thing that we've learned. So so just for this example, I'm going to look at the positive interior moment and trace this all the way through my moving load tracer. So in this instance, I'm looking at this controlling element of 1,00025, and node I is this controlling positive moment of this 280.25 kip feet. So I'll use the moving load tracer function, as Daniel mentioned. Just type in, I know this is the element that's controlling. It's at the I node, and I want to look for the maximum MY, so maximum moment. And then you can filter through the live load cases, or as Daniel mentioned, you can get an idea of what case is your controlling case by just comparing all of the moments in those cases. So I filtered through it, and you can see the 280.25 is my maximum value. So that's the case I want to pull for the static load cases. So I can then write that min-max case to a load file, save it as whatever I want to save it as, and then I can use the tools ribbon, the MCT command shell function, open it, and then run the case, and then it'll directly import that as a static live load case back into my model, which I can then run and verify that that moment matches what I expected to see in that 10025 element. It's at 280.25 kip feet. So now I have a moment with, so now I have that live load case with all of the corresponding concurrent loading, and it gives me the maximum positive moment in my cap. So once you go through that process, it's same as pulling for the dead load case. So you can pull all of the bearing element axial forces for the applied girder nodal loads, and then the column element axial shear and moment forces, and get your column reaction nodal loads for your strut tie model directly from the model with the static live load case. So here again, just pulling the reaction or the axial forces from those bearing elements gives me my applied nodal loads for the girders. And again, I applied the load factor to it before I put it into the strut tie model. And then same equations as I used to get my dead load column reactions will be used to get my live load column reactions from the axial moment and shear coming from that superstructure frame model of my Pier. And factoring these as well before I put them into my strut tie model. And same way, that's why the spreadsheet is super nice, because if you have, this is one of many live load cases. So it's easy to make a table and a spreadsheet and be able to just copy it and paste it straight into the MIDAS strut tie model. So you can have your forces. So then once you have all of your forces in the strut tie model, you can run the strut tie model. And then I've got post-processing spreadsheets, which help me analyze and run through all of the specification checks, as Daniel had mentioned, for the ties and for the nodal loads or nodal zones. So from the MIDAS strut tie model, pull out all of the truss forces and all of the elements, plop it into a spreadsheet, and then you can go through, all of these specification checks. So this is the first of the specification checks. And you may know this, but the rating factors, the condition factor and system factor of the structure multiplied by the capacity of the ties, which, as Daniel mentioned, the area of seal times the yield strength of the seal. Oh, sorry. It's my dog. Sorry. Okay, so the rating factor is just the capacity minus your demand from the dead load cases, and then divided by your factored live load demand. So the note that the area of the steel here changed for my case because we had more supplemental reinforcing over the columns. And so that, can vary, but obviously depends on the pier cap that you may be load rating. So then same process for the bottom core tension ties, same equation. And you can, apply or get the truss forces from the MIDAS model and then plop it into the spreadsheet and everything pops out. And then for the vertical ties, same equation as Daniel mentioned. So for the area of the steel for the vertical ties, it's based on the tributary width between the ties in the model. So depending on where your ties land, however many stirrups go to which element within my strut tie model. Note that the rating factor here is a rating factor of 0. We have noticed with the strut and tie methodology, shear can be a bit tricky, especially with caps that were not designed with strut and tie in mind. The sectional method may require less steel for the stirrups. So just something that we've run into. And then for the nodal zones, well, as Daniel mentioned, only the girder and column nodal zones generally need to be checked, only the nodes that are defined by a specific geometry. So if you have a smeared node, and it can essentially be as big as it needs to be, and you don't have to check it. So the girder nodes are defined by geometry based on the bearing, and then the column nodes are defined on geometry based on the column. So the capacity of the node is the limiting compressive stress multiplied by the effective cross-sectional area of the node face. And the limiting compressive stress is defined by the confinement modification factor multiplied by concrete efficiency factor and the compressive strength of the concrete. So note that if the pier cap does not contain crack control reinforcing, which is something we've run into when load rating caps, then the concrete efficiency factor is 0.45, regardless of which type of node is being checked. And the nodes are defined by the stresses which come into the nodes. So you've got the CCT compression, compression, compression versus CCT compression, compression, tension, or and CTT compression, tension, tension. So the node type may change with different live load cases too. So that's something to note. And then one approach that we've used is just to use a conservative value in the equations, so you don't have to change it depending. And then for each of the nodes, again, the girder nodes and the column nodes need to be checked. All of those nodes need to have a check of the bearing face, the back face, and then the strut to node interface. So for the bearing face, again, the geometry for the girder nodes is based on the bearing area, and then for the column nodes, it's based on the column width and depth. So bearing face checks compare the demand of the applied nodal loads at the girders and the reactions, those reaction loads at the columns to the capacity provided by the concrete area defined by the bearings at the girder nodes, and then the column at the column nodes. So, and then for the strut to node interface, as Daniel mentioned, you do have to resolve your forces if you have more than 3 compressive forces at each node. So we resolved it into the left and the right portion. So this is just an example of the right portion strut to node interface. So the geometry here is based on that resultant force, the resultant angle to that force. And then, so that's the geometry of the strut to node interface. And again, for a left and a right portion of every node. And then the last face is that back face. Generally, this is the controlling face that I. It's your lowest. It's the smallest concrete surface typically. So this was generally what was controlling for our cases. And one thing to note is this is why it can be part of an iterative process, because these nodes can be moved downward to better represent like the compression block that you're actually seeing in the concrete. But it depends where your tension versus your compression is. So if your node is at a place of high compression and you're failing some of these checks, you can move that node downward to better represent the behavior of the cap and to get some passing load ratings. But you need to be careful that it's not also a location of maximum tensile forces for a different live load case, because then your tie would be off center from where you need it to be to represent the steel within the cap. So, and then just to go quickly through the strut and tie model results. So these are all HL93 operating ratings. So the location of the HL93 operating ratings of less than 1.1, you can see we had bottom chord tension in these elements 31 and 32. So between the third and the fourth column, we had ratings of 1.05. Vertical tension, again, that's where I was saying the stirrups, elements 42, 48, 72, and 78. So these had HL93 operating ratings of 0. And then all of the strut and tie nodal zones passed that 1.1 threshold. So that's for this case what we saw, and then a quick comparison to sectional analysis results. So the controlling mechanism was shear in the left cantilever. We had HL93 operating ratings of 0.33, and in the right cantilever it was 0.84. So interesting that with the strut and tie model, we do not have any issues with the cantilevers, but in the sectional analysis, that's where our shear was the worst. And then we had torsion issues also, which can't really be, I guess, yeah, it's hard to load rate the strut and tie model with torsion. So Daniel mentioned some different methodologies that we use to just make sure that we have enough seal for torsion in the cap using strut and tie method. But this was an instance where, yeah, we just saw torsion pop up with the sectional analysis results. Still above 1, but less than 1.1. So obviously the sectional method in this instance produced higher ratings. The shear within the cantilevers controlled the sectional method, whereas the shear within the bays controlled the strut and tie method. So just a difference in the methodologies and probably how the cap was originally designed versus trying to use strut and tie methodology to analyze it. So that's what I've got for the presentation. I don't know if we have time for questions.
If you guys have time, we have a lot of questions. So if you guys don't mind, we can answer it. I just want to let the audience know really quick that we are recording the session. So for anybody who doesn't get to hear the question portion, you can always look back at it. Let me just take over really quick so that I can show everybody where they can find this presentation. Okay. Yeah, so if you guys go, are you guys able to see my screen?
Yes.
Yep.
Yes.
Okay, perfect. So if you guys go, like I mentioned at the beginning of the session, if you guys go to our midasoft.com/Midas Expert Engineers, under the event tab, you will be able to find all of our past webinars, including this one, posted on this site. So after this is over, we will be posting the recording of this webinar onto this page. So yeah, we have a lot, a lot of questions. So I'll just go ahead and get started. Give me 1 second. Okay, so we kind of set it, we split it up based on the questions we got per session. Okay, so the first question for Daniel Baxter that we have is, are you saying that the software such as RC-Pier that uses beam theory do not produce reliable designs?
Well, the code's is now recommending that for D regions that would include most Pier caps that strut and tie analysis be used, and that's what LRFD says. It's not that necessarily anything designed with beam theory would be wrong or was wrong. It's just this more updated code is just recommending that strut and tie analysis be used in its place. And I mean, certainly there have been cases of some Pier caps designed with beam theory where there was excessive cracking that most likely the strut and tie method would not have resulted in that. But that's not to say that like any Pier cap that had been designed with beam theory was necessarily wrong. But designing with strut and tie analysis does follow the recommendations of the current code.
Okay. The next one is, if there is a hammered node, where I'm assuming it's where is the axial/moment loads would be result in one of the nodes being in tension. Wouldn't the assumption of the column nodes at the 1/4 point be invalid?
Well, I guess that assumption of the 1/4 point, I mean, that seems to have worked the best for us, particularly with like smaller rectangular columns. With a larger hammerhead, if you have a wider column, I think you would want to look at that in a case-by-case basis, probably to experiment just to see if you move the location of that node in your strut and tie model, do the forces change that much? I mean, for like a hammerhead cap, one nice thing about that is if you just have a single column, the model is statically determined anyway, so you don't have to go through that whole process of computing the reaction loads from a frame model like we did with multiple column piers. So I would just, and even for multiple column piers, if you think that maybe the 1/4 point isn't the right point, just, I mean, just see if you change the assumption of where that node is and change your distance d that you use to compute those forces, like does it make that much of a difference in your forces? I think from our experience for multiple columns, it doesn't. But certainly for something for a wide hammerhead, maybe that's a little different. We have found that for really wide columns, let's say if you have something maybe like architecturally sized, a sort of wider wall that then supports it's a hammerhead or something like that, that actually using more than 2 support nodes can often give better performance, and that you would then find what the reaction forces are on the multiple nodes, just based on taking the moment and axial force at the top of the column, and sort of like you would with a pile group, computing the reaction nodes that way.
Okay, awesome. The third question we have is, isn't the 25-degree rule only between the ties and struts, not like the 6.2 degrees between 2 struts?
I think it's for
I think the 25-degree rules for everything. Like you wouldn't want to use a 6.2 degree angle, I think, between any two elements in your model, I think that just really wouldn't fit what I think the code recommends to do. So that's why we showed there's an example where say if you start with a model and you have two diagonal struts coming in from offset bearings and there was only a 6.2 degree angle between them, that's not what the code's encouraging. So we just resolved that into a single diagonal.
Okay. The next question we have is, why is the top right arrangement in slide 5 okay when the angle is greater than 25 degrees?
Let me try to refresh my memory about what's in slide 5.
Sure. Do you want to share your screen for it? Or
Yeah, sure.
okay, no problem.
Okay, I got slide 5 up.
Okay, sorry.
So
one
the
second.
question is that why is the top right okay?
The question is, why is the top right arrangement in slide 5 okay when the angle is greater than 25 degrees?
Oh, because well, we want the angle to be greater than 25 degrees. It's a 25-degree minimum rule. We don't want the angle to be less than 25 degrees. That's why the idea in the bottom left here, where there's a 17.4 degree angle, that we don't want that because that's too shallow in terms of how the struts and ties that intersect in a node. So up here we're much greater than 25 degrees, and if you measured the angle between the bottom tie and the diagonal, would be greater than 25 degrees too. So we're good.
Okay, thank you. Okay, so the next one is, what is efficient and inefficient in terms of a model? Is it does it come down to the number of nodes / members, etc.?
Am I still sharing my screen?
1 second. Okay, you should be.
Okay.
Try again. Yeah, there you go.
I guess one way you could define efficiency is, are you using the minimum amount of material to satisfy code requirements and provide a code compliant design? So, I mean, one way to think about that is this picture at the top left here that we saw, where just from the static, if say you just have a simply supported deep beam here with one load P, just from the statics of the truss, that half of that load goes to each support, and so that half of the load is going to appear in every single vertical tie. And since we take for a new design, since we take the force in the vertical tie and directly use that to size the amount of reinforcing, the right side of this deep beam is going to require 3 times as much vertical steel to transfer this load to the right support as the left side of the beam requires just a third of the vertical steel that the right would to satisfy the strut and tie requirements to transfer that load to the left support. So since on the left side we're making use of a third of the material to carry the same load as we are on the right, we're saying that's efficient versus inefficient.
Okay. Okay, so I'm gonna share my screen again, and these next 5 questions are for Shayla. Okay, can you guys see my screen?
Yep.
Oh, okay. Hold on, I think there we go. Okay, so the first question we got was, how do you define the cross-section area of the diagonal members?
Shayla, I think you're muted.
Shayla, yeah.
Sorry, thanks. I guess I'm not sure if this question is referring to the cross-sectional area for when you're doing the nodal checks of these diagonal members. So because we define the diagonal members as compression only, they should never be in tension. So we should never be doing, I guess, that area, or maybe the question is just meant to, so for the model, when I modeled the MIDAS elements, the area of the elements within MIDAS is just, it's like an arbitrary, I just use the same section and like section properties for the entire model. So maybe that's what the question was asking about. So it's just Yeah, I think maybe for that model, I just used like 1 inch by 1 inch cross section area for all of the members. It's just to get the truss model within MIDAS in order to get how the forces are distributed. So all of the sections have the same section properties within the model. Hopefully that answers that question.
Okay, thanks. Okay, so the next question we have is, in your model, the joints at the middle pier are not restraint against vertical moment. Then by applying column forces, these points will move, which does not match with the reality. This is why you get more tension at the bottom of pier cap than model with 2 supports. Oh, I think this is more of a statement than a question. Okay, I'll just skip over this one for now then.
I can
for
weigh
the-
in on that one.
Oh, go ahead.
Well, we've done some comparisons with this, and what the frame model is doing for you is the columns actually do deform under load. I mean, there's an axial deformation of the column and a bending deformation of the column, and that's why the forces are what they are in the frame model. I mean, if you went into the frame model of the columns plus the cap and put fixed boundary conditions at the top of the column or restrain the vertical movement of the column at the top, you'd probably get pretty different forces too. And I mean, you can look at the deflected shape of the strut and tie model once the nodal column reaction loads are applied. And I mean, if you've done the procedure correctly, it shouldn't be, I mean, its deflection should look reasonable. It should have it should have even deflections along its length. Like, it shouldn't be deflecting downwards more at the column nodes where you've just applied reaction forces versus where you've defined a boundary condition.
Okay, thanks. I think that definitely cleared it up for us. Okay, so then the next question is, for the frame model restrictions versus full support model, does that not make you lose confidence in the software?
Daniel, I don't know if you want to take that one too.
I can weigh in on this. I mean, it doesn't make me lose any confidence in the software, because I've seen that the forces change as I change my boundary conditions, and I'm just using truss elements in a simple 2D analysis model. I mean, I would be concerned if I didn't change the boundary conditions and the forces changed between 2 models, or it seemed inexplicable why they were changing. But I mean, in this case, I know that, on that slide that compared the 2 models, the top model, I defined fixed boundary conditions at each column node, and in the bottom model, I only had them at 2 plus the reaction forces, and they were consistent. So I feel good about that.
Okay. All right, Tatiana, I hope that answers that question. The next one we have is, how do you account for the additional tension in ties due to torsion?
So the way we've accounted for it in the past is by, like Daniel mentioned, using the equations in AASHTO LRFD to get the area of seal that you need for the tension if you have, or for the torsion if you have it above the threshold torsion, and then subtracting, I guess, that area of seal from our area of seal available for the vertical ties in the strut and tie model analysis.
Okay, and then the last question we have on this slide is, why did you put support at exterior piers? If we choose to put the supports on the other piers, will this result be different?
You can weigh in on that if you want.
Yeah.
I mean, we've looked at this, and it's statically equivalent. I mean, you can put those support nodes at any 2 pier reaction nodes that you choose. It should be statically equivalent, and you can that's one way to check that you're computing those reaction forces correctly. I mean, we just chose the exterior 2 ones for simplicity, but we can go in and look at the reactions of those supports, and they should match up exactly with what would be calculated in the spreadsheet that Shayla showed at those nodes. So you can put them anywhere you want. The key is just to have 2 of them to keep the model internally determined.
Okay, we have a lot more coming, so just
Oh,
bear
really?
with me. Yeah, we we have a lot. Okay, the next question we have, I think you can just disregard the top portion if whoever wants to take it is totally fine. But yeah, the next question we have is it okay? I'm sorry. Okay, it is greater than 25 degrees. Is there an upper limit or a greater limit?
I don't
I'm
think
assuming this is in regards to the 25-degree
yeah, I
rule.
don't
Yeah.
think there's an upper limit. I mean, certainly you'll have some 90-degree ones sometimes, or you could. So that's okay. Maybe there's some geometry where you could get a obtuse angle, but probably the only limit is that, I mean, you just need to have a statically stable truss. It's made out of like a triangular configuration of elements. So I think that's really your limiting factor there.
Okay, and then the next one is should not the model depend on the reinforcement configuration?
Oh, it does depend on the reinforcing configuration. As we discussed, for a new design, you're going to want to put the top and bottom chords of your strut and tie truss model at the center line of the longitudinal reinforcing that corresponds to those ties, and then the vertical ties, correspond to the vertical steel within the tributary width of each tie. So it's directly tied to the reinforcing configuration. And if you're analyzing an existing structure, the way Shayla was discussing, then you would need to put your ties to line up with the center line of the reinforcing groups in the existing structure.
Okay, perfect. Okay, and before I go on to this next question, we actually have like a little bit, I think right over 30 questions. So I think I'll just finish up this slide, and if it's okay with you guys, I'll email you guys the rest so we don't take up too much more of your time
Okay.
because we're a
That
little
works.
over time.
Gotta,
Is that okay?
yeah, that's good. There's a reinforced concrete
Okay,
arch
perfect.
actually.
Yeah. All right. So I think in that case, we'll just do one more and then I'll just email you guys the rest. So we'll just stick with number 3. So we can draw many different STM models for the same rigid structural element. What were your considerations that led to the OPT for this specific STM model rather than another one that would validate all the good practices for building a correct STM model?
Oh yeah, actually, I should be able to answer all 3 of these on the screen, and then I'll get back to our arch here. But like, I mean, one thing about strut tie analysis that I think sometimes will throw people for a loop is that there isn't necessarily one correct answer. I mean, the model I showed for that particular pier cap, I mean, met all of our requirements and practices, but I mean, potentially someone could come along and come up with another model that meets all those requirements and practices, and it maybe one of the models would result in a slightly more efficient design than the other, but they'd all satisfy the code requirements, and they all would produce a safe, code compliant design that also met serviceability requirements. So there's not necessarily like one correct answer in all cases. I mean, at least we found with pier caps that, I mean, if you put, I mean, with your 2 support nodes per column and your bearing nodes and your nodes placed where there are girders, girder bearings, I mean, typically that in itself plus the 25-degree minimum rule will limit the number of possible solutions you can obtain. But certainly there might be some slight differences between 2 compliant models, and that's okay.
Okay, awesome. So then we'll just run through these last 2 really quickly then. On your model, we can see that you define the vertical bearing reactions, but how about the horizontal ones? Did you apply them on your STM model or not? If not, why?
Sorry if you missed that. We include the horizontal reactions too from the shear at the top of the columns. That, I mean, and that shear can just be due to the deformation of the columns plus cap from vertical loads, and it can also be due to transverse loads such as wind loads. So we include that in our process too. And sorry if I didn't point that out enough the first time around.
Okay, and then the last one is, did you use the same STM model for the strength combinations and extreme event combinations?
Yes, sorry if I didn't make this clear before, but the strut and tie analysis procedure it's at the strength limit state, so that you use factored loads at the strength limit state to design your steel and do your nodal checks, and with that, and then the serviceability checks are that shear span check for minimum section dimensions and the crack control reinforcing. But it's primarily done at the strength limit state. That's where you do your design and would work for an extreme event limit state too.
Okay, I'll just email you guys the rest because we do have quite a lot and I don't want to take up too much of your time. But yeah, thank you guys so much. This was such an amazing webinar, very, very insightful. I know our audience definitely enjoyed it. I know I enjoyed it. So yeah, thank you guys so much. I don't know if you guys have anything else to say. No?
I don't think so. Thanks everyone for sticking around.
Okay, all right, awesome. So in that case, that concludes our session. Again, thank you to everybody who joined us today. Thank you for everybody who stuck around. We're gonna put this up shortly on our MEN page, as I demonstrated earlier, so you can look it over again. And yeah, have a great day. Thanks.
Thank you, Daniel. Thank you, Shayla. Have
guys.
a nice day.
Thanks.
Thank you,
Have a
Daniel.
good
Thank
day,
you,
guys.
Shayla.
Bye.